Muito bem, hoje, dia 9 de setembro de 2021, nós estamos iniciando a gravação desse colóquio no Departamento de Física da UFSCar, hoje com a presença muito ilustre, muito querida do professor Alberto Guimarães, do CBPF. Eu quero... So let me ask, is there anyone in the audience that would not follow if the colloquium is given in Portuguese? Doesn't seem to be so. So I leave it up to Alberto decide whether it goes in Portuguese or in English. It's going to be, a record forever. So if you wanna send it to your friends abroad.
Okay.
Mas, de qualquer maneira, fique totalmente à vontade. Como ninguém se manifestou, eu tenho a impressão que todos vão seguir bem se você falar em português. Todo mundo domina o idioma aqui. Eu quero formalmente apresentar Alberto Passos Guimarães, muito conhecido das velhas e das novas gerações, alguém que trabalhou uma longa jornada em magnetismo no Brasil, tem livro escrito, tem contribuições importantes na literatura e está já como é que eu vou te chamar? Qual é o seu rótulo? Aposentado?
O teu enfeite emérito.
Esse é mais legal, então. Como eu não sabia, te devo os parabéns que oferece automaticamente nesse momento. Então, mas ele continua ativo em ciência e vai nos falar hoje sobre Skyrmions magnéticos, que é tema das suas pesquisas atuais. Nós vamos deixar a audiência à vontade para fazer perguntas, desde que elas sejam rápidas e que possam facilitar para quem está fazendo a compreensão do que está sendo dito, deixando, evidentemente, a critério de cada um decidir se vale a pena interromper ou deixar as questões para o final, quando, após a exposição, o Alberto, então, vai à disposição para respondê-las. Muito bem-vindo, Alberto. Você fica com a palavra, com o vídeo, enfim. The floor is yours.
Okay, well, thank you very much, Ortiz. I will speak English in view of the fact that you told me you had invited some foreign colleagues, so I'll do it in English, but if there's any doubts about some slides, I would happily answer the questions that may arise. Okay, well, the first thing I would like to say is that we should always take into account we are going through a very tragic side of our history, with the last evening numbers, 584,000 dead people in Brazil. So we have to keep in our memory that we have lost so many men and women in this country to the pandemic. Now, proceeding with our talk, these are the aspects of the problem that we will deal with. First of all, a description of the types of skyrmions and the properties of the skyrmions and applications. Well, skyrmions, most of you already know, are some small structures, nanoscopic structures, or vortex-like nanoscopic structures that have been discovered, predicted many years ago, and discovered some 10 years ago. Okay. The discovery of the skyrmion gave rise to very many articles in magazines, science magazines, predicting and describing the properties and the hopes that the skyrmions would add as part of the toolbox in spintronics, with the unique properties of the skyrmions, many applications and many new effects were expected and have in fact been discovered. I will show, already exploring possibilities that the skyrmions present, and the impact in spintronics will be felt in the next few years. It all started with an article on nuclear physics in 1962, where Sturm himself, the first author, wrote a paper with some concepts that were relevant to problems in nuclear physics, but they appeared to contain general aspects that would be shared by other domains of physics. In our case, of solid-state physics and magnetic properties. This article has had its importance in nuclear physics, but it expanded, it had its influence very much wider than the nuclear physics. These are some images of the magnetic skyrmions. They look as shown here as circular objects, like shown here, these two types, and they are represented here are the magnetic moments in different sites of the skyrmion. This is a different vision of the same skyrmions. On the right, this is called the Bloch type, and this is the Niel type of skyrmion on the right. They, as a cross-section, you can see along the diameter that the magnetic moments, they turn. In the case of the Bloch type, they turn outside the plane of the equator here. And in the Niel type, they turn inside this plane. This is a property of these two that characterize these two types of skyrmions. In one case, tangential to circles, and others in the radial plane. Related to these skyrmions I've just shown, there are some 3D structures, more complex and less well studied so far. These are the hopfions, shown here on the left, as these donuts covered with the magnetic moments. More recently, there has appeared this skyrmion bundle, as shown here in the figure, a 3D structure that on the surface shows, on the cross-section, it shows what appears to be normal 2D skyrmion. And more recently, this skyrmion braid, this also 3D structure that has been proposed very recently. This is an article of this year. Okay, as I said, the skyrmions were predicted in 1989 by Bogdanov and Dzyaloshinskii. They predicted the possibility of vortices being stabilized in some magnetic structures. And this was 1989. In 2009, there was the first experimental observation of the skyrmions of a group in Germany, and this was published in 2009. The first experimental observation found a skyrmion lattice, as shown here, a regular lattice with many skyrmions. The lattice skyrmion was observed before the individual skyrmion appeared. The skyrmion has one of the most important properties is the topological protection. The topological protection is very basic and very important in the skyrmion, and this implies that the skyrmions they have an energy barrier that has to be overcome if a foreign agent affects the skyrmion. For example, a magnetic field or an interaction with a defect on a solid. They may challenge the stability of the skyrmion, but there is an energy barrier related to its topology that guarantees a certain stability. It's easier to understand this topological protection if one considers domain walls. Here I show on the left a domain magnetized towards the right, on the right a domain magnetized towards the left, and in the middle a region known as domain wall, an intermediate region where the magnetization takes an intermediate direction. This the domain has some aspects in common with the skyrmion and may be easier to visualize what one if we treat some properties of domain walls. This is an example of several structures, vectors organized. Think of these as magnetic moments organized on top of a circle, and these several structures are characterized by a winding number or vorticity, shown here. For example, in the first picture on the left, we see arrows that are all parallel. If we start on the north pole here and turn around the anti-clockwise sense, we see that these arrows they do not turn, so they turn 0 radians once we follow the circle. If we move to the second picture here, we see a vector pointing to up, and as we move along the circle, the vector turns. And when we return to the same position again, the vector, it has turned its direction clockwise, counterclockwise in the first half, and in the second half, clockwise. Therefore, the overall angle that changed was 0. Just like in here, the angle that the arrow turned in the end was 0 in both cases. This characterizes this winding number. The winding number is this angle in radians divided by 2 pi. As we move here to the third case, now the vector, as one turns counterclockwise, it turns, and it turns in a counterclockwise sense as well. Therefore, as one returns to the top of the circle, we have had an angle of 2 pi. Therefore, 2 pi divided by 2 pi is 1. So this is the case of a winding number 1 and winding number 2 and so on. This winding number is, if one adds effects, out of plane effects, for example, if one includes the polarity, which is the direction of the magnetization at the center of the structure, in the case of the skyrmion. Therefore, P could be plus or minus 1. If we multiply this winding number by P, we have the topological charge, which I will mention several times along my talk. This topological charge is the important measure of the topology of the skyrmion. And the topological protection means difficulty in changing the topological charge. But as I said, this is more obvious if one considers domain walls. For example, here I have a linear magnetic solid represented by these arrows, and in the middle I have one arrow pointing in the opposite direction. This is a defect, and this is it's called a local soliton, and this is a trivial type of defect because one can destroy this effect by turning one single moment. On the other hand, if we had a structure that is, in fact, a domain wall, we have the magnetization of the first half pointing upwards, the second half downwards, and we cannot destroy and transform this into a ferromagnetic linear system by acting locally. We have to act on the whole of this sample. In the real life, if this were a sample, we would apply a magnetic field and we would expel this, magnetize the right half of the sample upwards, and then we push out the domain wall, and in a finite sample, we can correct this, apply the field, we destroy this effect. But with an empty sample, we cannot do that. So in the first case, acting locally, one destroys the soliton, and in the second case, a local change cannot destroy the soliton. Okay, now let's move to a more complex situation. Now I have one domain on the left, one domain in the middle, downwards, and one domain upwards in the air. And I have a domain wall here, the intermediate region between these two domains on the left, and the second domain wall. Now, if you watch carefully, you see that the magnetic moments on the right, they turn in the clockwise direction into the second domain, whereas between the second domain and the third domain, now the moments turn in the counterclockwise direction. So the overall winding number, if we add these two problems here, regions, it's zero. The total winding number is zero. And it could be otherwise. It could be the same. They could turn perhaps in the same sense, as shown in the second magnetic sample. Now, within this wall, the moments turn clockwise, and in the second wall, they also turn clockwise. So these two, they cannot be easily destroyed. They have a total winding number that's not zero, a winding number that's not zero. And the fact that this gives an extra stability is easily seen in a simulation. I will show you here, this paper by Kunz and co-workers. Here we have three domains, 1, 2, 3, and the domain wall is not very clear, but the domain wall, the moments inside the first domain wall, they turn counterclockwise, the blue circle and blue arrow. And in the second wall, they turn clockwise. So this is a micro-numerical simulation or micromagnetic simulation. And the image B, C, and D, these images correspond to the same system under an applied magnetic field, a magnetic field that would tend to destroy this wall, destroy the domain in the middle and the two walls. So we see varying the time under the influence of this applied magnetic field, the intermediate region, the intermediate domain practically disappears, and we reach a situation of one single domain. Now we are going to show what happens when this was a case of zero widening number. Now if we have the two domain walls studied differently, as shown here, now they turn one in one sense, the other in the other. Sorry, both in the same sense. Both in the same sense. And now in the simulation, the same applied field observed, the sample observed after the same time led to this result shown on the bottom right here. That is, the intermediate domain was not destroyed. So this is a demonstration that clearly shows how the topology protects this structure in the middle, it guarantees the presence of this intermediate magnetized towards the left region. So this is it's clear to demonstrate then that topology helps in the protection and in the stability of a magnetic structure. Sorry. Well, in this in the description of this magnetic system, especially in the case of this micromagnetic simulation, which is a numerical simulation of some physically interesting magnetic samples, we use the main components, the main energy terms that are required for a proper description are the exchange interaction, which is responsible for the existence of magnetism or magnetic order, the anisotropy energy, which normally has crystalline origin or other kind of origin, shape origin or different origins, and this interaction, which is perhaps new to some of you, the Dzyaloshinskii-Moriya exchange. This is a type of exchange where the parallelism of the moment as expressed here in the Heisenberg exchange, it does not exist. Here is a vector product. So here the energy is minimized when the magnetic moments, the operators here, but the magnetic moments as well, they are not parallel. So this Dzyaloshinskii-Moriya exchange favors a non-parallel alignment of the magnetic moments. And the images I have shown already, but I will show in the next slides. They were obtained, most of them, from these numerical simulations using these terms in the Hamiltonian. In this micromagnetic approximation, these terms are included, and the system looks for an energy minimum or a minimum torque on the magnetic moments of the different cells that the physical system is divided into. Okay, now this is a representation on the right here of the Dzyaloshinskii-Moriya interaction. These are spins 1 and 2, and depending on the direction of this vector d, the arrangement of the spins is somewhat different. In the case that we have already shown of the two main types of skyrmions, Bloch skyrmions and nail skyrmions, each one is related to one type of expression for the Dzyaloshinskii interaction. This is another representation of the skyrmion. Sometimes a color code is used. This is, in this case here, blue is up and red is down. In other cases, to be black and white as well. Okay, this interaction is found in non-central symmetric crystals, and crystals that have like an inversion center, and there are also it also appears in interface. So there may be a contribution of DMI from the bulk and the contribution from the interface. This DMI is usually present in systems that show Skyrmions, but more recently the systems without DMI but exhibiting geometric frustration were discovered. Frustration is in simple terms the effect where the different magnetic moments are not all pointing in a minimal energy direction. There's no arrangement that satisfies this minimization, and this is, in simple terms, geometric frustration. Okay, now other forms of classification of the Skyrmions. These are the same again that I have already shown: block type and AL type. If we follow how the moments turn along the radius, in this case here, they turn out of the plane where this cut was made. They turn out of the plane and they turn by pi radians from the rim until the center is reached. This is a pi type Skyrmion. The snail type here is also a pi type Skyrmion, because again, this time within this plane, they turn, the moments turn of pi radians. Other types of Skyrmions exist. For example, this Skyrmion is a pi Skyrmion. It's the most common type of Skyrmion that one sees in the literature. And you see the moments they turn from here to here to the center, pi radians. This is the common Skyrmion. Another type of Skyrmion shows a different geometry. The moments now turn through pi from the rim to the center. This is a 2 pi Skyrmion, also known as skyrmionium. The topological charge here is 1, and in this case, the topological charge here is 0. This second type of Skyrmion, the skyrmionium, is also known in the literature as target Skyrmion, because it looks like a target. Okay. More complex Skyrmions can turn of an angle of 3 pi or 4 pi or more. Okay. Other structures are also known in the Skyrmion family. This is Skyrmion, an anti-skyrion. It's similar to the anti-vortex that was also studied in the last years. This anti-skyrion has also been observed experimentally. Now, one playing with the parameters that I mentioned, the perpendicular anisotropy and Dzyaloshinskii-Moriya interaction, one can study what happens as we change these two parameters, K, Z, and Dint. These parameters measuring the magnetic anisotropy and measuring the Dzyaloshinskii-Moriya. Varying these parameters, we find several pairs that allow a stable fermion to be formed. And this can be shown in the phase diagram that I would like to show you. This large region here is formed of only single domains. This image shown on the right here, single domains. So for the whole, this whole area of the plane is formed of only single domains as stable structures. This was the result of micromagnetic simulation. Each time for each pair, simulation was made, and the minimum energy configuration was plotted here. Here we see this is the work of one of my collaborators, Dr. Vigo Cotrina. We know if we examine what happens for this line here, the anisotropy given by 1 megajoule per cubic meter. As one moves here, varying Dint, we find first this skyrmion, this red symbols. The green symbols are 2 pi skyrmions. The blue symbols are 3 pi skyrmions, 4 pi, and finally 5 pi skyrmions here. So all of these structures appear, are favored when we move, we vary this Dzyaloshinskii-Moriya interaction, keeping, in this case, fixed the value of the anisotropy. Now, among the most interesting properties of the skyrmions, one of the most interesting properties is that the skyrmions can be made to move through the influence of the electric current. This is a very important paper by Albert Passos group. He shows here skyrmions moving in the top sample, in the top case here. These are simulations, of course. In the top simulation, 1 mega ampere per square centimeter, the current density, electric current density, and on the bottom case, 5 mega ampere per square centimeter. 1 mega ampere in electric current, it's a lot, but in terms of area, these nanostructures are very, very, very thin. Therefore, this does not mean the number is large, but the density is large, but the current is not large. It's a small current. So we see in the bottom here that the larger current induces a faster motion of this skyrmion. In this paper, they have shown as well that the skyrmion has the ability of avoiding defects. Any nanostructure prepared in the laboratory will have defects, and if the skyrmion has the ability of avoiding the defects, in this case, not. This is very important in application. Therefore, in the real world, samples have defects, and the skyrmions may avoid this and show do not pin themselves at this defect. Here is another example of skyrmion in motion. This is a skyrmion also simulation under the effect of the electric current, and this slide shows a very important effect, that the skyrmion usually does not move parallel to the sample parallel to the sense of the electric current. They tend to deviate from a straight line. This is known as skyrmion Hall effect. It's one of the new effects observed with skyrmions. This is the simulation is with a pi skyrmion that has Q equals to 1, showing that in this type of skyrmion, this effect is observed. A deviation from the straight line, which is in principle inconvenient for application that require the motion, devices that require the motion of skyrmions. This is an example of several are shown here several examples of what happened to these different types of skyrmions. On the bottom here is the skyrmion of the type shown in the previous slide. This shows it's a normal skyrmion, a pi skyrmion. It deviates from the horizontal here, meaning that as one proceeds in the nanowire, it moves away from the axis. Now a different type of skyrmion, a skyrmionium here in the middle with Q equals 0. This is a 2 pi skyrmion. It does not deviate. It proceeds along this horizontal line. And also on the top, some of these skyrmion bundles that I have shown, which have very large Q, they indeed have large angles of deviation. This here shows the angle for these three kinds of skyrmions. The first one, minus 60 degrees, the skyrmion, the pi skyrmion. The 2 pi skyrmion, 0, as these bundles where there are many skyrmions have a large angle, 60 degrees. So the skyrmion Hall effect is interesting, and it can be observed in a large family of skyrmions. Okay. Another effect that was observed for the first time with the skyrmion is the topological Hall effect. This is a skyrmion in a ferromagnetic plane, and current is being introduced in this skyrmion with this electric field E here. As the electrons move into the skyrmion, they interact with the moments of the skyrmion, and it appears that when this interaction of the electrons is with some chiral structure, an extra magnetic field appears, this so-called emergent B field. And the final effect is that this chiral structure selects and the electrons spin up and spin down. The spin up go to one side of the sample and one side of the skyrmion, and the spin down to the other side. So it's another kind of Hall effect that was observed with the skyrmion. This is the topological Hall effect that arises entirely from the topology, the different topology of the skyrmion. One of the applications that attracted the attention of workers in the area was the use of skyrmions in racetrack memories, as I will show more in detail. These are some magazines, 2017, 2021, 2020, claiming that the skyrmions would be very important for a new generation of memories, the so-called racetrack memories, have this name due to the shape. The racetrack memories were first proposed at IBM in 2008 by Stuart Parkin, and they essentially are described here in this image. The red and blue regions are regions magnetized along different directions, and a current circulating through this racetrack sample pushes the domains and the domains, and the information is written and read at the base of this structure. So the information being bits 0 and 1, 0 domains in one direction, and blue ones domains in the other direction. So this is the racetrack memory, designed originally in 2008 to use domains and domain walls. Different types of racetrack memories have been suggested. This is a case of a linear one, a magnetic strip with domains in one direction and the other direction, and the write head and the read head in the same way, the same principle of this racetrack. In fact, the suggestion was, original suggestion was that the racetracks could be stored in a 3D geometry like here, and this would mean higher density memory, and a memory that would be easily accessed by other electronic components of a system. Oops, sorry. With the discovery of the Skyrmion, there was made a suggestion that the same system would operate with Skyrmions. Now here, the Skyrmion, the presence of the Skyrmion corresponds to the bit 1, and the absence of the Skyrmion corresponds to the bit 0. So this would be analogous to the domain wall racetrack, but made of Skyrmions that would be displaced by the current, as I have shown. Okay, now after the suggestion with the Skyrmion was made, in the literature there was a surge of articles comparing the properties of Skyrmions and domain walls in the racetrack geometry. And here we see the graph of driving currents, here, this axis, and velocity. And we see this linear dependence here, showing, it's not very obvious, but there are two lines, two straight lines here, one in black and one in blue. Sorry. The black line corresponds to the behavior of the domain walls, domain wall racetrack, and the blue lines and the points correspond to the Skyrmion. So as we see on the whole, the dependence of velocity with current density is identical in the two systems, in Skyrmions and domain walls. But as we analyze the beginning of this curve, this inset, you see the behavior is very different. The Skyrmion, with a very, very small current, they start to move, as described in this blue line here, whereas the domain wall does not start moving until the current density reaches a threshold value here. So the domain wall is pinned more strongly than the Skyrmion. Therefore, the domain wall, to move, it has to surmount a barrier that keeps it pinned. This is shown here as well. This is a periodic function, voltage, or no, current function, periodic like that. And for very low values of this current, the blue point marks the pinning current of Skyrmion. The Skyrmion starts to move here, whereas the domain wall will only start to move once the voltage reaches this value here. So the simulations and experiments have shown that there is an important advantage here. The pinning of the domain walls means that the domain wall needs a larger driving current to start its motion. This is a comparison of two types of memories using this principle. On the top, it's a domain wall memory, now in this linear geometry, not a racetrack anymore. But here you see blue, blue, red, blue and red are the zeros and ones, and here the equivalent piece of electronic device containing skyrmions. Now here the skyrmions are zeros and ones here. There's a one problem to measure the zero in the case of skyrmion, because the system has to know exactly where to look for a skyrmion. Because looking for a skyrmion in this region, there won't be found. The system will not measure a skyrmion, and this will correspond to a zero. But this, it's not well defined, the position of the zero, as it is well defined the position of the opposite domain. This is one problem for the skyrmion, but there are ways of solving this problem. Here, the skyrmions show another very interesting property. Motion goes from the left to the right. For example, here I have two domain walls. One system magnetized in the red direction or in the blue direction, and as time goes by, this domain move, and once it reaches wider magnetic system, it becomes a skyrmion. Therefore, one could have electronic devices where manipulation in one part of the circuit is done as the manipulation of domain wall, and in another part, the manipulation would involve skyrmion. They are easily transformed. Domain walls are easily transformed into skyrmions. Here is the opposite. Is reversible the system. Once one starts with skyrmions applying the pressure, the current, then they move and they become domain walls. So one could devise spintronic equipment where, for certain functions, it would deal with skyrmions, for other functions, it would deal with domain walls. There are some advantages of dealing with domain walls and some advantages of dealing with skyrmion. And this case shows that they are convertible, which is very important. Here are several quantities are described. One of them is the Q, the topological charge. It changes, and as one moves from skyrmion to the domain wall. Okay, this mobility of the skyrmion has led to many proposals of applications. The racetrack geometry was one, as I have shown. The other possibilities are to, in this case here, to deal with skyrmions and use the bit 0 corresponding to a skyrmion that moves on the left track, and a bit 1 when it moves on the right track. So there are some gates here, which essentially mean regions of high anisotropy, induced anisotropy. So a circuit could close the gate or open the gate and fill one track or fill other track. So this could be something like that. The skyrmion comes in, finds this gate open, it moves like this, it's counted as a 0. If it moves through the right-hand track, it's counted as a 1. So this is an evolution from the racetrack memory, and it is a technically viable thing. And in the micromagnetic simulations, it means that it requires that a certain region has changed the anisotropy to allow to block the passage of the skyrmion. I have to go faster, I see now. These are several, in the literature, several comparisons of the qualities and the properties of the domain walls versus the properties of the skyrmion. Here, the size of the skyrmion rated as 10 to 50 nanometers. The domain walls 20 to 50, not much difference. The speed can be skyrmions of the order 100 meters per second. The domain walls can be faster, 500 to 750. The critical current is the very important and difference that I have brought your attention to. The critical current for skyrmion amperes per square centimeter, this is about 100, whereas 10 to the 7th power for domain walls. So in terms of critical current, the domain walls are 10 to the 5 worse than the skyrmion. Okay, here is another rating of comparison of domain walls and skyrmions. The very many qualities like energy density, etc., cost, the architecture benefit, and so on, topological stability, and critical depending. They're the only one here that the maximum velocity is maximum velocity for the same current, but the higher current, the domain walls move faster. Okay, these are modifications of the original track, memory skyrmion track. These are 2 tracks, and to update this value here, for example, there is this bridge that connects the 2 tracks, and one can modify one single skyrmion without going through the whole complete set of skyrmions. In the original racetrack, one has to read the whole set of skyrmions to modify one. Here, with this cross contact, one can modify one single skyrmion. Another variant of this track is application as a gate, a logic gate. Here there are two inputs. When there is no input here, no input there, and there's no signal in the output. Now, when there are 2 skyrmions, they meet here in this joint, and they merge. So this is an example I put in the literature of processing in racetrack principle. 2 skyrmions, they merge and become 1 skyrmion. So this truth table for the logic, this logic gate is given here as well. Okay. I mentioned in the last slides, I have mentioned the motion of the skyrmion, but the skyrmionium, as I said, it does not deviate, does not present the skyrmion Hall effect, and the fact that it does not deviate from laterally is interesting. Also, the skyrmionium shown here in red, this is velocity, this is current density. It goes faster than the original skyrmion, which is given here in blue. And another effect that appears with skyrmioniums when they are under large current is that they distort, and they may be destroyed with the application of current. So this is apparently a problem, but can be used in some systems to destroy or erase the skyrmionium, increase suddenly the current and then destroy the skyrmionium, and it produces zero answer on the other end of the circuit. Okay. Other logic gates, much more complex, have been devised. This geometrical object here, this is a magnetic circuit in red with this detailed dimensions as shown here. This is a gate that has a length of 600 nanometers, and it has, this is shown here, how it operates. It's an AND gate with, I'll show one in a simulation here. This is a gate with the one skyrmion on the left hand gives no output. Here, one skyrmion on the right gives also no output, as it should, because inputs 0 and 0, 1, 0, and 0 and 1 should all give 0 output. Whereas when the skyrmion, when there is input in both ends of the structure, they naturally go through, and 1 and 1 gives an output of 1, as it should be in an AND logic gate. So these logic gates are very interesting and intelligent applications of the skyrmion. Other applications, I'll go rapidly through them. This, with the skyrmion here, a spin current going through, this is a magnetic nanodisk, a spin current going through induces the motion of the skyrmion, and the skyrmion is read by this reader here. This is a tunnel junction. The resistivity of the system varies once the skyrmion goes to its base here, and the result is the motion of the skyrmion is this. It starts from the center and then turns. Every time it passes through this reader, it gives the signal. Therefore, the output is this high frequency in the gigahertz region. So this is an oscillator that uses the motion of the skyrmion. Another application. Now I will deal rapidly with one application where I have been involved with my colleague, Dr. Dzyaloshinskii-Moriya. This is how to create skyrmions or skyrmioniums from single domain, for example. This is the results of the magnetic simulation. We start with a single domain, and we can obtain from the single domain a skyrmion or a skyrmionium by exciting the single domain with some frequencies of the spin wave frequency of the system. Here are the spectra of skyrmions and skyrmionium. There are several peaks in this frequencies, and what we can do is apply this frequency more favorably, applying the frequency of one of these peaks to the single domain, and then we generate either skyrmions or skyrmionium as desired. These results show, under the application of the three frequency modes, this is a graph of topological charge, modulus of Q versus time. This is 3 nanoseconds, and for several frequencies, one column for each frequency, and we see that all of them, either of these frequencies being applied, they all lead to a topological charge of 1, which is modulus 1, which is characterized of the skyrmion. Therefore, any of these peaks chosen leads to the production of one skyrmion. This is the evolution of the image of the disk after, in this case, 4 nanoseconds, almost 8 nanoseconds. And the other possibility using frequency of the skyrmionium is generating a skyrmionium. In this case, with time, exciting with any of these three modes. One of them, this time Q equals 0, which characterizes the skyrmionium. And here are the images of the disk after 4 nanoseconds. We obtained the target structure that characterizes the skyrmionium. Another application along the same line of this oscillating magnetic field, it was the application of inverting the polarity of the skyrmionium. Starting with skyrmionium with the white region here in the middle, we end up with the black region. The white region is magnetized upwards, MZ positive, and here's, sorry, negative, and this MZ positive. Therefore, applying this frequency of this mode, one can invert the frequency. And this is the switching of the skyrmionium, which is certainly useful in many memory devices. The possibility of the same graph of MZ at the center. Okay, I'm running out of time now. So these are the images again, and this is a video showing the evolution of the magnetization on the face of the disk, reaching the final structure with the black dot in the middle, as shown here in this graph. So with this, I finish my presentation, emphasizing that skyrmions are topologically protected nanostructures, that the formation of these skyrmions is favored by Dzyaloshinskii-Moriya interaction or geometric frustration. Skyrmions can be classified as the form that the magnetic modes turn along a diameter in AL or Bloch type, or the angle that the magnetization turns, 1 pi, 2 pi, 3 pi, and so on. Skyrmions may be displaced with small current density. Skyrmions are associated to new observed effects, such as Skyrmion Hall effect and topological Hall effect. Applying oscillating magnetic fields may be used to switch the magnetized disk into a skyrmion or a skyrmionium. There are many proposed applications for skyrmions. Example, racetrack memories, logic gates, nano oscillators, transistors, neuromorphic computing, and so on. Well, these are the names of our collaborators, and I thank you for your attention.
We thank you, Alberto, for the nice and comprehensive presentation. And so we have now the colloquium is open for questions or comments. Well, I don't see anybody willing to pose a question. So I have one. Actually, during your presentation, I was wondering if it would be appropriate to ask what would be the most appropriate media or concrete media where you create skyrmions. And then one of the recent slides, you show that your simulations were using cobalt platinum, was that?
Yes.
So yeah, so it was nice to see that you have a preference. So what would be the parameters that would lead you to pick one material instead of any other? I mean, at a certain point, you show a kind of a diagram where you have different terms of the Hamiltonian of the model, and then you can create this or that. So what is good for you know, hosting a skyrmion? isotropic materials, or on the contrary? Can you comment on that?
What do you think? Property materials?
Yeah, I mean, if I were to start a plant to produce skyrmions, what would be the best choice?
Okay. Well, I don't think anyone should start an industry of my advice, because I don't know the details of the compounds. It may be cheaper to produce, easier to produce, and so on. But ideally, one would look for systems that have anisotropy and systems that have this DMI interaction, which, as I said, can arise either from an interface, like a cobalt on top of another metal. That interface may give rise to the DMI interaction. And the anisotropy may be the way you crystallize the disk of magnetic material. You have a built-in anisotropy that would allow the appearance of skyrmions. There are many systems that have been suggested, bilayers or multi-layers, that experimental work has seen skyrmions in very different systems. They all have to have this property, absence of central symmetry. And there are now many systems where they have been observed. Other things would have to come into play, like the temperature. One needs to, I didn't say much about temperature, but to be a practical application, you have to be able to run at room temperature, of course. And the skyrmion lifetime is also related to the temperature. Many experimental observations were made at room temperature, but some skyrmions may be they would be more stable at lower temperatures, of course.
Mm-hmm. But lower, you mean nitrogen, liquid nitrogen, or
Yes. No, the simulation, most of the simulations are made at T equals 0. But they can be seen at room temperature. They have been seen at room temperature. So, but their stability is related to the temperature. This is for sure.
Yeah, I didn't have a chance to read the paper that of yours with Vigo Cotrina last year's, which results you have shown today. So those are only simulations, or is there any experimental result on that?
No. Of our part, no experimental results. We have done. This is pandemic-proof work.
Yeah, but the idea would be to excite with a perpendicular field in a frequency that is compatible with the magnons.
Yes. Mm-hmm. That's the idea.
So it wouldn't be difficult to put it into practice, right? For a laboratory that has these apparatus.
Yes. No, it wouldn't be difficult. No.
Mm-hmm. Great. Well, a last chance for questions or comments. If not, we thank again Professor Alberto Guimarães for sharing with us his expertise and experience on this subject.